I'll be the next speaker once I have my slides up. And actually, it's a project that we have been working on for a while, and it will definitely use the column database. And that's one of my personal motivation of contacting Mark and John in UCLA and trying to revive SPD, because we need such development in this project I am about to present to you. This is the so-called BRACE2, which stands for Bridge Rapid Assessment Center for Extreme Events. It's part of the Peer Bridge program that's funded by Caltrans. And before I start, I would like to acknowledge, as I said, we have been working on this for about 3-4 years now. The current project manager is Claudio Perez, who's finishing his PhD. He should be somewhere here. Yeah, he's right here. And we have several PhD students working on different aspects of this project. Isaac, Guanrin, Winhow, that they are also somewhere here. We get a lot of administrative support from Peer, taking advantage of being the director. So Amarnath and Gabriel have been very helpful. And in phase 1, we started phase 2 last February. In phase 1, Crystal Churn, who's sitting here, was leading this effort, and she got rewarded. She got a PhD out of it, so that's not too bad. And we acknowledge the Caltrans support, and also the Department of Conservation through the California Geological Survey, and specifically the SMIP, the Strong Motion Instrumentation Program, because they share their data with us in real time, and that's important for this BRACE2 platform that I'm about to discuss with you. So the overall goals of this BRACE2 effort is to enhance the resilience and safety of California bridges, integrate technologies like digital twins, machine learning, real-time data streaming into a robust platform for structural health monitoring of bridges. For that purpose, we focused on designing a web-based platform with modular components to encapsulate complexity, enhance reusability, and simplify system maintenance. All the things a good database developer would need to be putting in front of their eyes. Otherwise, a little bit later, things become obsolete, and you have to redo a lot of your coding or the tools that you have. If they don't continue to function, then we haven't achieved the intended purpose of longevity of this platform. So the outline of my presentation, I'll briefly go over what was the motivation of developing this BRACE2 platform. And we paid a lot of attention to the used methods and the abstractions we wanted to build this platform on. And then briefly, I'll talk about some of the important completed outcomes and some of the important current progress items. And then I have some concluding remarks. So in terms of motivation, Chris Trena, who's sitting here, shared this with me some time ago about the instrumented bridges in California. And there is 80 of those distributed over the 12 Caltrans districts. District 4 takes the largest number. It has 30 instrumented bridges. And you see them distributed on this map here with these blue dots. So this is very important part of the Caltrans assets that can tell us about what is going on in these assets, because there is a sensor there that reads something, and we would like to make full use of such readings to learn about Are we doing well in our modeling? Are we utilizing this data to its fullest? And to show the capability that, hey, there is another 2 orders of magnitude of these assets that are not instrumented. Should they be instrumented, or that's enough? Is that 80 a representative subset, or we need to add more and put more resources in the instrumentation program? So the word smart keep coming, and I used to dislike it, but now I like it. I think smart. We should speak about smart infrastructure. It can be viewed in many different ways. BRACE2 view it as structures that have sensors that can tell us about the vibration response. So it's accelerometers that on these structures that give us data and tell us about some information. So that's the focus of BRACE2. That's why you see this BRACE2 logo here in the 3rd column. But smart can also include other type of data modality. It can include things that involve images or videos. It can include even text. After an earthquake, there will be a lot of not tweet anymore, X's or whatever they call it now, about this Facebook. People are going to put things in social media about what happened to bridges they cross on daily basis, or their children's school that is shut down, or a hospital that's not operational. So this social media data is also very useful. BRACE2 platform is designed to eventually incorporate such different data modality, not just the vibration. At the moment, we are focused on data that SMIP would deliver to us, either directly or indirectly. But in the future, we would like to see, or we are hoping to include things related to vision-based deep learning or text-based natural language processing, such that BRACE2 can truly provide a link between decision makers, engineers, and also researchers. So I mentioned in my opening remarks about the Peer Bridge program that was just get renewed as of yesterday, as you saw in the news. There are 7 topical areas covered by Peer Bridge. The first topic is maintenance and sustainability, which has the objective of develop cost-effective methods for assessing the structural health of a bridge. The 7th topic is intelligent design tools, bridge design aids, with the objective of develop new tools to take advantage of AI to accelerate bridge design process. BRACE2 is fill the objectives or satisfy the objective of these topical areas, 1 and 7. And then the other areas you see listed there where other projects cover that. So in terms of the methods and abstractions, and here I go very briefly because we can spend quite a bit of time talking about what went on in the past 3-4 years in that regard. So if you go to our platform, which is still at the moment is not publicly open, you would see a page that lists all the events. Events here means the different earthquakes that these bridges have been exposed to. And then there is a list of the assets. These are the bridges that have these instruments or have a model that represent their response. These models, we call them predictors, and you can have several of these models. Some of them are based solely on the data. Others are based on a physics model, on actual digital twin that can get updated with the data. What do these predictors do? They conduct evaluations. And what do these evaluations lead to? They develop metrics, such that these metrics inform us about what happened to the system or what might be the decision that follow this response. So Going just one by one of this terminology. So we started with an inventory. What are the bridges we are going to look at? Of course, we started with those that are instrumented. And this thing, like mushroom, it grew in our backyard. And we started looking even at bridges that do not have instrumentation. So each bridge in the inventory, we call it an asset. So the asset in the inventory is represented by a digital twin, and digital twin has many definitions. We follow this definition, which is a virtual representation of the asset, which in this case is the bridge, that persistently mirrors the state, context, and behavior of that asset. The digital twin is updated with real-world data, enabling real-time monitoring and predictive analysis. Currently in BRACE2, and this will change in the future, we have what we call a full digital twin and a partial digital twin. And that's our own classification. Partial digital twin is a digital twin that only uses the data to develop the model. And a full digital twin is a model that is not only based on the data, but also based on a finite element model, based on some physics, some geometry and material properties, not just what the accelerometers are telling us in terms of input and output. So we have this distinction here, whether we have built the physics-based model or not of that asset, then it falls into the partial digital twin. If we have built it already, then it makes it a full digital twin. An asset profile would represent the information that's related to this asset with several evaluations. So for example, here, each evaluation page will combine several predictors for a single event. So for example, you can envision several classes of finite element modeling, or several ways of handling the data on the bridge, several methods of system identification. Each of those is a different evaluation and will lead to a different set of metrics. So each of these predictors is responsible of several metrics within the evaluation page. So for example, one of those predictors may be able to give you information about the column drift, or give you information about the superstructure maximum acceleration, and so on. So the predictors page will manage all predictors for a particular asset. So you have a particular bridge subjected to a set of input motions from different events. So then this bridge could be configured for different predictors. So for example, here, one bridge may have different system ID models that you see listed here, SRIM in the transverse direction, or Okidera DC in the transverse direction, and so on. Or it can have a finite element model, as I put in this red box, which could be a CSI bridge model that's part of this predictors list. So the predictors come in two flavors, what we call type 1, which is what most engineers will do, build a finite element model of the bridge, include idealization of the abutments, whether they include some springs for the soil, model the piles or the deep foundation. And they need information about the mass, the stiffness, the damping, the input acceleration, in a typical finite element model, whether it's done in OpenSeas or done in CSI Bridge or any other platform an engineer would prefer to use. So that's what we call type 1 predictors. If we have this built for a particular asset, it will raise it to be a full digital twin. If we only have a data-driven model, which only takes input motion and output motion and try to find the state of the asset, So in that case, we use state space model or any of the methods that people use for system identification. That's what we call type 2 predictors. And that will only apply to bridges that have instrumentations. Right? So why we decided to have these two types? Because each one of them has its advantages and disadvantages. So type 1 is typically a high fidelity. Of course, if you have the right geometry and material properties and take into account the soil properties and so on, but it could be very time consuming. There is a large workforce that use this approach. But careful modeling is needed because you need more information to put into your model. It produces intuitive metrics that engineers and researchers are used to, but it needs careful interpretation. And that's what we spend time on, and this ties to SPD, because basically we say, okay, we can compute column drifts, we can compute maximum peak quantities, whether it's velocity, acceleration, and so on. But will these things be useful in terms of quantifying damage? There is information available in the literature that can do damage classification, different damage states, as you see at the bottom here. Damage state 1 from cover cracking all the way to core shedding and even beyond until columns collapse or bridge collapse. So there are tools that we have built in platforms like OpenSeas that are calibrated with test results and other information that we can make use of. But will this be useful following an immediate earthquake in terms of bridge inspection and making a decision? So Caltrans has a fantastic document called First Responder Bridge Assessment Guide. It classifies what happened to bridges into 4 categories, R1 to R4. R1 is to keep the bridge open, which means everything is fine. R4 is the opposite, close the bridge immediately, which means something really, really bad. And R2 and R3 in between. So one thing we spend time on is to try to relate these damage states, 1 to 5, as you see in the bottom here, to these R1 to R4. But did we do a complete job on this? The answer is no, because we need an intermediate step. We need the 400 plus columns on SPD to relate these damage states to actual experimental observations and then make more educated decisions on how these observations translate into this decision making. So that's my main interest, Mark, in asking you to help us with SPD so we can do a better job here. For type 2, hey, you have data coming from bridge. We will be fools if we don't make use of it. So that's what type 2 metrics are, is to complement type 1 if we have them, because they are easier to configure. If you know what is your input, what's your output, that's an easy thing. If you have a little bit of knowledge about state space methods or system identification, which plethora of methods exist in the literature for that. It's a faster to evaluate. So Crystal spent quite a bit of time encapsulating the most important methods into one open source Python library for system ID. It's called MDOF. And it uses, this type uses real response of the structure, which is the sensor data. By the way, it can also use synthetic response. So if we don't have sensors and you have a high fidelity finite element model, you can use your nodal responses as your virtual measurements, if that's the best you can do. Typically, it requires some specialized training. So this shows the architecture of MDOF, and this list here are the different methods that are implemented in MDOF. It's open source. It resides on the web. You can download it from GitHub. But if you do, acknowledge the PhD of Crystal, please, because she spent a lot of time on it. So it can show results like this, looking at the Fourier transfer function, frequency content in a windowed way. And this is for Painter Street for the Petrolia event back in 2023. And a lot of other outputs you can get from this tool. So briefly about completed outcomes, the dashboard is complete, which give you asset prioritization according to the recent events. Every earthquake creates an event in the event table. Currently, the platform has 295 evaluated events that you see them clustered here in this map. And originally, we started with 5 bridges. And then at the end of phase 1, we extended that to 22 bridges. And then we went wild after that. Now it has 2,359 bridges that are included in our assets. So the word pilot doesn't qualify anymore. So each of these assets, basically we grab everything available in the web from FHWA. So it has all the information that's available for each of these assets. You see a sub-list here in terms of longitude, latitude, in terms of the some geometry, number of spans, type of abutments, and so on. Again, we are preparing that for eventual use with something like SGMD, because now knowing the longitude and latitude, we can go and grab the ground motion from SGMD and subject it to that particular, if that of course exists in the San Francisco Bay Area, or when SGMD extend to SoCal as well. In terms of the predictors, we have 160 tailored predictor for the 22 assets at the completion of phase 1. But now this extended to 2,359 automatic predictors. What is the difference between the two? Tailored predictor is a predictor that is configured manually, meaning somebody sat in front of the platform and put the input channels, put the output channels, and selected a particular method for system ID. So that's a tailored predictor that's already configured, and there is 160 of them. The other large number is basically we took the hazardous fragilities for all the bridges that we have included in the platform, and also included these fragility functions in the platform, such that if you know your spectral acceleration, you can have an idea about the probability of damage of that particular bridge. That's a placeholder until we configure some of the other predictors, whether they are data-driven or physical model. And we have a tool that you can add your new predictor. So you can just go to the predictor generator, choose the method, choose the channels you want to use as input or as output. Some of the other things that Claudio has spent time on is to enhance the digital twin rendering. This is Painter Street, which has 11 predictors already configured. This is the Hayward Highway 580-238 interchange. So we're spending time to make that platform also user-friendly. In terms of current progress, as I said, we started with 5 bridges. We extended that to 22 and now 2,000 plus. We just added one full digital twin based on a CSI bridge model that Caltrans engineer shared with us as a test case on how we get a physics-based model done by an engineer, how this can be included in the platform without us building it from scratch. So that's something we're experimenting with. to extend this real-time data streaming. We have been working with CGS to increase the number of bridges that are monitored in real time. Currently, we only have 2 of them, the Hayward and the Riodale or Painter Street. So we hope to have that number grow in the future. And the other thing we are working on, I mentioned about NLP. So now we have a tool within the platform that following an earthquake event, we can produce a short report that makes use of the bridges that have instruments to tell us what happened to these bridges and generate automatically a report. We did that last Christmas after the Cape Mendocino earthquake that affected some of the bridges we have in BRACE2. Other ongoing work include several things related to modeling, several things related to assessment, exploring critical modeling features of the current and the future digital twins, thinking about abutment contribution, for example, implementing new predictors as an uploading mechanism, where, as I mentioned, Caltrans engineer has a CSI bridge model, wants to upload that as a new predictor of one of the bridges. We are working on streamlining this better. In terms of assessment, prioritizing the metric presentation. You can compute a lot of things, but how do you prioritize those such that when somebody look at this as an end user, get the most useful information first? New insightful presentations of the supported predictors and their evolution with events. We're starting to see some of these assets seeing more than one event now. So we can actually look at the history of these predictors from one event to the next. Painter Street is an example. And here I will predict next Christmas there will be an earthquake in this place because it happened 2 times in a row. So we should get ready, at least for Painter Street and its surrounding bridges. Claudio is working hard to make our ecosystem open source, available, documented well. So we have a whole array of pieces of code that we make available, and people can go download them. We just ask you to acknowledge the source. And finally, a few concluding remarks. BRACE2 is a web-based platform interacting with several other databases. We expect this to grow with more databases you heard already in the previous presentations. It currently has several partial digital twins and 2 full digital twins. We think these numbers will grow significantly in the coming few months. The computed BRACE2 damage state is based on this Caltrans First Responder Bridge Assessment Guide and hazardous fragility functions. We expect significant improvement of that, especially with the enlargement of SPD and other data sets. BRACE2 include a lot of data-driven models for excitation, response, type of system ID, and also for like transfer functions, and also methods based on state space realization like Kalman filter and so on. The computational ecosystem of data and simulation in BRACE2 for structure vibration analysis is general, and it's not limited only to bridges, even though this is funded by Caltrans, but there is no reason this cannot be used for, especially like some of these pieces of code would not be used also for buildings or tunnels or other parts of our C-grade infrastructure. The ASE report came out this morning, and it's a C grade. I think we can do better with smarter infrastructure and more instruments. Thank you very much.